Greetings everyone and welcome back for another exciting lecture in geomorphology. Today we're going to continue our discussion of soils and build on that by looking at the different soils we find in landscapes throughout the planet. So that's our plan today. We're going to be looking at types of soil as this peat farmer over here is digging out a very particular soil type that is very useful for a particular tasty beverage that we'll talk about a little bit later today. So you should have already watched the first video where we talk about what a soil is, why it's important for geology, how we can describe the morphology of a soil in terms of its structure, in terms of its color, in terms of its texture. And now we're building on that. Oh, sorry, we added one more thing. We also added the CLORPT approach. Hans Jenny came up with a very important system, the soils factors approach, for letting us think about the different variables that are going to influence the soil, whether that be climate or organics or relief or parent material or time. CLORPT allows us to think about the factors that influence how big the B horizon is going to be, how big the A horizon is going to be, whether there's going to be calcium carbonate in the soil or if it's going to be something else. So now we're going to build on that by taking CLORPT, taking our morphology of a soil and thinking about the different soil orders out there. Okay, so here we go. We've already done this to a certain extent, excuse me, when we've talked about in our last lecture about kind of the broad differences in the horizons from a forest soil to a grassland soil to an arid soil over here. So arid soils are going to have very, very, very small O horizons and very big B horizons. That's going to be different than, say, which way do I want to go? Yeah, let's go this way. A grassland soil. So in a grassland soil, it's a bit drier than a forest soil. So we accumulate organic material in the A horizon and we get B horizon. That would be different than a more humid forest soil where we have relatively thin A horizons, but we have the development of those E horizons, which is where we get maximum weathering and eluviation, and then we have the B horizon below that. Okay, so that's kind of what we're building on. We're going to build on that and explore the different types of soils all around the world. And I don't care where you are, whether you're up in Alaska or down in South America or over in Africa or over in Australia, you should be able to, no matter what soil you find, not sure if you can hear that squeaking behind me, Doolin's back there. No matter what soil you find, you should be able to classify it into one of these groups up here, one of these following groups. All soils you can classify into these groups. So that's what we're going to be talking about today. The broad soil orders are going to be controlled based on climate. We can think about climate being kind of a first order control on the different formations of soil. So here are all the different soil orders right here, all the way from really cool vertisols, which we're going to learn about in places like Texas, to gelisols all the way over here. So when you think about soils, we're going to be thinking about them in formation from more dry climates to more wet climates, and from more dry to wet climates, and then from cold climates over here over to more warm climates. And so that's kind of how we can break down and think about soils. And so that's going to tell us something about the formation process, right? So an oxisol over here in the warm and wet area, may this be a soil where we're going to see intensive chemical weathering? Great thought. I completely agree with you on that. I think we just might see that. Okay, so kind of the key here is that soils vary with climate. And so when we think about kind of climate, thinking about kind of on our x-axis, walking across the screen here, being latitude, where right now I'm at the equator, we're at the equator, and then marching from the wet equator, tropical areas, towards the temperates, and then all the way to the cold, dry poles over here. We can think about what we see for soils, and then what we're going to be looking at is what types of material we see in the soils in these different latitudes, using these as a proxy for climate, right? And so polar deserts, temperate zones, those temperate mid-latitudes, dry deserts, in the subtropics, and then the wet tropics, savannas of the equator. So what we generally will see is that we're going to see, we talked about this in chemical weathering, that you're going to see the formation in thicker soils all the way, let me flip here on you. So we're going to get greater soil depth and greater weathering in these wet soils where we have more warm temperatures and water for weathering. And then as we dry out, we're going to see very thin soils, and then that bumps up again as we get to the temperate zone, then moving up to the dry poles again, not nearly as much soil development. So we're looking at here also kind of based on climate and degree of weathering where you're going to be producing kaolinite versus illites. And remember, we talked about these in iron oxides in reference to climate, that the types of clays and iron oxides are going to depend on the degree of weathering in that weathering environment. Excellent. Okay, so let's move on here to this soil system. So the system we're going to be talking about is the soil classification system used in the United States today, but there are some others as well. So the modern system, it gets its approach from, if we think about how a soil forms, we can think about it either in terms of a genetic approach, and in a genetic approach, we're talking about kind of the genesis of the soil. How did the soil form? What are the soil forming processes? So that would be a genetic approach, and that's going to be kind of really different than a morphologic approach. So morphologic approach, where you're describing and classifying soils based on what they look like. Our US system is based on the morphological, the described measurable soil properties, whether that's the amount of organic material in the A horizon or something else. It's going to be based on those described soil properties, but it has very strong, look what it says here, very strong genetic underpinnings, that those morphological properties that we use to classify the soils are related to a specific soil forming process. So this system is really developed for soils that were observed within the US, but we can apply it globally as well. So the soil system is a hierarchical system. And so at the highest level here, we have 12 orders of soils. And then within each of those 12 orders of soils, based on different variables like climate or amount of water in the soil, we can get to suborders of soils, and then suborders we can further divide into great groups, subgroups, families, all the way down the soil series, which is greater than 15,000 of them. So today I think we should get through most of the soil series. So that's really only about 15,000 soils we should get through. So I think we can cover that in, got me, or I got you maybe. No, we're of course not going to go down to this level, not in a brief lecture on this. Today we're going to start with the major soil orders here, the top level of categorization of soil. So that's going to be our plan for today. So when you get back to campus, and it'll happen sometime soon, what you are going to learn about, or you'll see on the wall, I've got a poster. There's a poster here of the 12 orders of soil taxonomies. Go check that out. But let's get through these here. Okay, so when we talk about the soil order, there's a couple parts to the names of the soil. So there's the formative element that's at the beginning, like ent, and then we have a connecting vowel, like I or O, and then we end it with sol, which is soil. So a gelisol would be a arid region soil, or an entisol would be a soil with minimal profile development. So the first part kind of describes what the soil is. We connect the vowel, then we just have the last part telling you it's a soil. Okay. So soil names, as you start kind of going farther down that hierarchical categorization, yes, okay. We had those formative elements. We have the formative elements like an entisol, and so we take that formative element, the ent, and then we add that at the end of our subgroup or great group name. So a fluve aquent is a soil that the fluve tells us that the parent material is related to rivers and fluvial deposition. The aqu is that there's a lot of water availability in the soil, and the ent tells us that it's an entisol. So we can start to break apart really complex soil names by just kind of identifying these different parts of the soil name. Okay, so the system here in the U.S., it's been refined over the past 50 years. Um, and really every soil order should have the same meaning for everyone. Um, and the key here is that this system, you should be able to do a pretty good job of going out in the field and observing these properties, but they really need to be replicated in a laboratory. To officially name a soil, you really need to go back and make measurements of the amount of carbon, calcium carbonate or something else in the soil. Okay, so there are essentially 12 orders. There are, not essentially, there are 12 orders of soil in the US taxonomic system. And these are basically designed based on the presence or absence of certain soil horizons. We're going to take a brief break here. The dogs are going crazy. I'm going to go check on that, and I will be right back. Okay, and we're back. Sorry about that. We're going to continue our discussion of the 12 soil orders and kind of the broad differentiations between each of these soil orders and the characteristics you find in them. So that's our plan here. They really, as I showed you in the previous slide, oftentimes are related to climate and the temperature and the precipitation in a region, and that's going to drive kind of soil forming processes that will place any particular soil into one of these broad soil orders. Okay, so let's go through these really quickly, one by one, and then what we'll do is we're going to come back to each one and talk about them in particular. So the first here is a gelisol. So you can think of these as cold region soils. These are soils that have permafrost or material that melts and then refreezes very close to the surface. Okay, moving down from gelisols, we have histosols. So histosols are going to be soils that have significant amounts of organic matter within the A and O horizon. So we call these histosols. Below that are spotosols. So spotosols, we'll talk about what these are. They have a spotic horizon. These are going to be associated with those big E horizons and cold regions and forests. Andisols that have andic properties, so these are going to be associated with volcanic processes. Oxisols, where we see extreme weathering. From oxisols, let me move away a little bit, where we'll have our vertisols. And so vertisols are soils with lots and lots of clay in them, so we're going to have lots and lots of shrink swell type of features in vertisols. Moving down from vertisols are iridosoils, and so iridosols, excuse me, iridosols are dryland soils, so we've already talked a little bit about those. Below that are going to be ultisols. So ultisols are kind of humid region soils where we have significant amounts of weathering and generally drive these to be fairly acidic soils in our ultisols. After that, we're going to have mollisols. And so mollisols are our big grassland, big A horizon soils. So they're going to have a mollic epipedon. Let's just say for now that what we're talking about here is a big, thick kind of dark A horizon associated with mollisols. And our alphasols are going to be other soils like these that don't have necessarily the degree of development of any of the other properties here, but they do at least have an argillic horizon or something like that, so some sort of horizonation. Inceptisols are going to be our youngest soils associated with just a small amount of soil forming processes, which gets us to our all other soils. These are our entasols, and they're just barely a soil. We can just barely differentiate between an entasol and just a geologic deposit. So those would be entasols down here on the bottom. Entasols. Okay. So where do we find gelisols? So the distribution, not surprisingly, where we find gelisols is in our cold regions. So gelisols are in cold regions where we still have permafrost. Generally, because of the cold temperatures with these gelisols, we don't see a lot of weathering, and so you don't see a lot of horizonation development that proceeds with time. Really, these we stack up large amounts of organic material, and we get a lot of wetting and melting at the surface with permafrost under gelisol. Um, some of the cool things associated with gelosols are going to be associated with our periglacial processes, permafrost processes, where we're going to get really cool pattern ground features like you're seeing here, the picture here, and that's associated with essentially melting of the surface of the soil during summertime, but you still have permafrost at depth, and so that water can infiltrate down below, percolate down below, and so it stays at the surface, and you get kind of these swampy soils. You get these cool patterns that gelisols contain a large amount of organic material, lots and lots of organic material in gelisols, and that's because of the fact that essentially the soils freeze and they're fairly wet, and so you can't have a lot of decomposition, and so the organic material, then any tundra vegetation that's growing, when it dies, it can't decompose, and so you keep stacking it up. So you'll have lots and lots of O horizons here. So those are gelisols. Notice here I also mentioned that these things store a lot of organic carbon. So this is a concern when we think about climate change. As we start to warm up gelisols and move them out of the gelisol category where they're not freezing every year, we have the potential for decomposition of that organic material in gelisols, which will add to already increased carbon, CO2 in the atmosphere. Okay, moving on from our gelisols, we have histosols. And so histosols are where we have essentially restricted drainage so that we have waterlogged conditions all the time. And when you have waterlogged conditions, you can't get any decomposition, right? We can't get oxygen in to break down the organic material. And so because of that, with a histosol, what happens is you just end up with a big, thick pile of organic material. When you think of histosols, think of these big, huge organic horizons, big, thick organic horizons. We associate these with things like peat bogs. And so with our histosols, they're often waterlogged, and so they have limited uses for building on because they have so much water in them. As you drain them out, they compress. Interestingly, with histosols, because of all that organic material, these are actually used. They're mined for both fuel and agricultural purposes. You can burn that material. And of course, one of my favorite uses from the first picture of the textbook, other uses of histosols, not only can you use in a peat bog, you can cut out part of the histosol and you can use that, you can dry it and use it for, you can use that for burning. You can heat your house with it. But you can also use it for smokiness and using basically the burning of the peat. When you're talking about the grains used in, say, Scotch production, that smoky flavor of Scotch is related to using histosols as the source for heating those grains, which then give that nice smoky flavor. Okay, so as I mentioned with histosols, these are waterlogged soils, and so as we drain them, you oftentimes will see subsidence as the histosols start to compress. So the picture here is from the Everglades, and what we're looking at here at the top of this, right here, that used to be the soil surface. The land was right here. And what's happened over time as we've taken the Everglades and drained them so we can develop them and build parking lots and Disneyland and things like that, you lose that water and the histosols start to compress and the land subsides down. So this is what can happen with. Okay, often with histosols you end up with a lot of potentially gray colors in them because of them being waterlogged. So this blue color down here, this is reducing conditions associated with glaying, and so we get those blue-green colors then up and oxidized horizon. You have those more orange colors, so you get glaying in your sols. Okay, moving on from histosols, we have our spotosols. Another word for these are acid soils, and the key feature here is something called podzolization. And so what that is you can actually get the accumulation of iron oxides and aluminum oxides down in the B horizon. And so these are essentially chelated, and we're not going to get into the details here, but when you have strongly acidic soils, you can make these chelates where we can actually dissolve organic material and move that down into the B horizon. And we're moving down organic material and those aluminum and iron oxides. So where do we find these? You find these where you have acidic soils, like under conifers in cool forests. Okay. Um, so our spotosols here, this kind of is your classic look of a spotosol. You'll have that classic E horizon eluviation, and then we have a fairly small organic horizon on top. But then look down here in the B horizon. The B horizons are really interesting. Um, Notice all these um, dark colors here. That's organic material that is translocated and eluviated out of the A and O horizon and moved down and deposited in the B horizon, associated with those iron and aluminum oxides. Um, these are generally nutrient poor soils, and so they require a lot of fertilizer if you're going to grow in these things, as you've moved essentially a lot of the nutrients out of the top of the soil. So these are spotosols. Okay, moving on from spotosols, another one that people love and is very common in our part of the world in the Pacific Northwest, those are andesols. And andesols, it's really hard to see where you have them on the map here, but you can Google it and have a look. You're going to find andesols where you have lots of active volcanoes, like say the Pacific Northwest is where you have them. And so andesols are formed by layers and layers of volcanic ash, and you kind of, with that ash, you'll get glassy material, right? Because when stuff's erupted out of the volcano, magma, it cools really quickly, and you can't grow crystals, and so you have glass, and so you have glass and ash that dominate these soils. And you'll find andesols up in the Blue Mountains outside of Walla Walla here. Because of all that ash, these are generally high water holding capacity soils. And these can be very, very nutrient rich and soils, and they're actually really good for growing crops. They're able to fix large quantities of phosphorus. I don't want to go into the details of what that means now, but what this means is that with andesols, with andesols, you get essentially really, really nice soils for growing crops. And of course, that can be a really, really big problem, right? Because where do you find the andesols? Next to active volcanoes. So oftentimes we see around the world that people develop close to active volcanoes. One reason why is because soils are so good. So those are andesols. Okay, moving on from our andesols, we have oxasols. Where you look for oxasols are going to be in those equatorial regions. Equatorial regions where we have high temperatures and lots of water. So because of that, we can do massive amounts of chemical weathering, extreme chemical weathering, where we produce oxides, and we basically weather away most of the mineral material, except for, say, the quartz. And so because of that, you have very, very low soil fertility in oxasols. So you get often these bright red colors associated with oxasols, and that's because you're deeply weathering the parent material, and you're producing iron oxides. So in an oxasol, because of that, most of the vegetation associated with, most of the nutrients that would be in an oxasol aren't in there. They're taken up into the vegetation that's above in the forest canopy. So the soils themselves end up being very nutrient poor. And so kind of a classic example of where you can see this is the Cerrado region here in Brazil, where we have lots and lots of extreme chemical weathering. Let's skip over this for right now. Let's just keep moving on our main soil order so this video doesn't get too long. We can come back to slash and burn in our discussion. Next up in our soil orders are vertisols. And so vertisols, remember, those are our ones with lots of clay in them. And so we're going to get lots of churning of the soil associated with wet and dry seasons. And so maybe in the wet season, your soil expands up. And then when it dries out, you get large cracks in the soil, so you can churn these soils and you get deep, wide cracks. And so shrink swell is really an important part. And you'll find these vertisols in locations where you have lots and lots of clay in the soil. So again, here's kind of that churning here, and you get these mud cracks. This is just showing like what precipitation is going to look like in a region where you're having lots of vertisols. You want to have that distinct rainy season so that you can saturate the soils and get them really wet, and then dry them out during the dry season to form these big cracks. Generally in vertisols, you don't see a lot of well-developed horizons because of all that mixing. And you can actually see slicken sides in the soils on the bed faces. And maybe you haven't had structure yet, but slicken sides are where you're actually having movement of material and you kind of scratch one material against another, like in a fault. Here, we're just moving the clay against the clay, and you can actually kind of make these lines in it that we call slicken sides. So that's really common in vertisols. Another word for these are self-mulching soils. And by self-mulching, what that means is they mix really well because you develop these big cracks and the material falls down into the crack and then it gets mixed in and then you repeat the whole process. And mostly I just like using this slide because I don't know why, but there's a squirrel that's about to fall into this crack here. But also the slide is really cool because it shows that difference with the wet season. So here's the wet season right here when the soils kind of expand. And then as we move into the dry season, we get those big cracks that develop. Okay, moving on from our vertisols, we come next to our aridosols. These are dry land soils. And so dry land soils are with generally kind of, we associate them with with no O horizons, small A horizons, and very thick B horizon. And so because it's so dry, we see minimal leaching. So once you weather material or add material into the soil through dust additions, that material will stay in the soil profile in the B horizon because you can't flush it out. It's never wet enough to flush that material out of the soil. And so you can end up with things like petrocalcic horizons, which in the picture here, BK, K stands for calcium carbonate. Because you can never wet these soils enough to flush this stuff out, that stuff just accumulates and thickens over time. Same with the clays. We see B stands for alluvial clay. We see lots of clay in aridosols because, again, we make the clays or they come in with the dust, and then you just can't flush them out. So big, thick B horizon in our aridosols. Okay, moving on from our aridosols, we have what are known as ultisols. And so these are kind of, we generally get these in humid climates, but not quite humid enough to make an oxisol. And so in our ultisols, we generally have low soil fertility again because of intensive weathering that acidifies the soil and makes these fairly nutrient poor. So again, in the United States, where we see lots of these are the southeastern United States. So again, we have extreme weathering, so you're leaching out, you're removing a lot of the calcium, magnesium, potassium elements that plants like, and so that makes these generally nutrient poor. And so you need a lot of fertilizer if you're going to using these soils for agriculture. Okay, our mollisols, as I mentioned earlier, mollisols are our grassland soils, and so they're going to have a big, thick, dark A horizon. And these are generally very good fertile soils, good for crops. So in our part of the world here in the Pacific Northwest, in the Palouse Hills, we have lots and lots of big grasslands and mollisols. Again, look at the sizes. We get those big, thick A horizons and all that organic material, very dark colors with the accumulation. On the dry end of mollisols, you end up, because they're dry enough, you end up with calcium carbonate as well. So you have BK horizons as well. Besides the Pacific Northwest, I should also mention that this is the dominant soil order in the Great Plains as well. Okay, let's skip the questions for class. All right, our alpha sols are moving on. Alpha sols are where essentially we're getting down to like, well, if it's not one of the others, it has to be one of these. And so alpha sols are soils that we see in temperate and humid regions, but they don't have spotted horizons. They're not as nutrient poor as a blasted, weathered ultisol. They don't build, they're wet, so you don't build up that organic material like you do in a grassland sol, a mollisol, and so we end up with what's called alpha sol. And so these have fairly high soil fertility, and we find these in humid to some humid regions. So kind of in the Midwest here, kind of in the the Ohio, Pennsylvania areas where you can find lots of alpha sol. Basically, a lot of the world's population is supported on alpha sols, and so because of the temperateness of the regions, kind of what these guys can look like: relatively thin O and A horizons and fairly thick B horizons. So these are fairly good soils for growing crops in. Okay, so inceptisols essentially are soils that are just forming, that don't have any of these classic characteristics of any of the other soils. They lack these features of more well-developed soils. So you might have an A horizon and then maybe a W, which we stand for weakly developed soil profile development, in a B. So just not strong horizonation. And then finally, our last horizon is our most recent soils, what we call entasols. They really lack any genetic horizons anywhere. So you'll see these in places like the Sahara Desert, where you have not much, where you have relatively young soils without a lot of moisture for weathering to produce soil horizons or vegetation. So again, just barely a soil here. So again, it's not all C. It might have the incorporation of some A material. So we have to call it a soil, but it doesn't have any of our other diagnostic horizons. So we just call it an entasol. Sorry about that. Maybe it's the boringest of the soil horizons, but it's certainly the youngest generally. So where do you see these? Would be here, where you maybe have recent alluvial deposits and stacking up, and we just have stabilization of the surface and a little bit of vegetation growing on it, and we develop that little baby A horizon. Okay, that's it, y'all. Congratulations, you made it through the 12 soil orders. You should be really proud of yourself for getting through that. These are incredibly cool. They're all really different, and I encourage you to kind of look through and explore soils in a lot more detail. So thanks very much for watching. That's all I got for you now. We'll see you soon. Enjoy it. Bye. Also, gotta say it, don't treat your soils like dirt. Soils are important. All right, now I'm really leaving. Bye.